Probability is just a ratio of the number of specific events that give us an outcome that we want. And then that number of events is divided by the total number of outcomes possible. So if we have a probability equal to 1, the event that we're talking about will always occur. If we have a probability equal to 0, then the event we're talking about will never occur. Halfway between these, if we have a probability equal to 0.5, then the event we're talking about has an equal chance of occurring as not occurring. Now you can have probabilities of 0.67, you can have probabilities of 0.21. The numbers always range between 1 and 0. If you have a probability of 0.67, then you have a pretty good chance of the event you're looking at of occurring. If your probability is 0.21, then the event you're talking about probably won't happen. It might, but it probably will not. So the closer you get to 0, the less likely your event is going to occur. And the closer you get to 1, the more likely your event is going to occur. So let's look at a simple example. What is the probability of tossing a coin and getting heads? Well, remember, probability is the number of specific events that we're looking at over the total number of outcomes. If I toss a coin, I might get heads, or I might get tails. Those are the only two possible outcomes. So the total number of outcomes, that's equal to 2. Now the number of specific events, this is the number of ways we can get the result we're looking for. And the result we're looking for is getting heads. Well, there's only one way that can happen. That's when the coin lands heads up. So there's only one way that can happen, then our numerator would be 1. So our probability then, that's equal to 1 over 2, or it's usually expressed as 0.5. We got a 50% chance of tossing a coin and getting heads. Now sometimes you're not given a probability of an event, sometimes you'll be given the odds of an event. Odds are a lot like probability, but there's one small difference. If we're talking about the odds of an event occurring, call it event A, then that's the number of outcomes that we're looking for. And instead of the total number of outcomes being in the denominator, it's the number of outcomes that are not what we were looking for. So again, if we were flipping that coin and we wanted to get heads, there's only one outcome, and that's when the coin lands on heads. But instead of the total number of outcomes being in the denominator, we count the number of outcomes that do not give us the result we're looking for. Well, again, it's either heads or tails. So there's only one outcome that doesn't give us the event we're looking for, and that's when the coin lands tails side up. So our denominator would be 1. So the odds of flipping a coin, that would be 1 over 1. Or sometimes you'll see odds expressed as a colon, a 1 to 1. Now sometimes you'll see odds expressed as the odds against the event you're looking for from occurring. Well, that's the same thing we did up here. It's just the reciprocal of the ratio we were talking about before. In our numerator, we have the number of outcomes that are not the event we're looking for, and in the denominator, we have the number of outcomes that are satisfying the event we're looking for. So in this case, if we wanted the odds against getting heads when we flipped a coin, then we'd have the number of tails occurrences, which would be 1, over the number of occurrences, or the number of heads that we might get, so 1. So let's work through some other examples of odds, or finding the odds. What are the odds that an ace is drawn out of a deck of cards? Well, if we have a standard deck of cards, there are 52 cards in that deck. And again, if it's a standard deck of cards, then there are 4 aces. So if we're talking about the odds that an ace is drawn out of a deck, well, then we need the number of occurrences in the numerator. Well, there's 4 aces, so there's 4 different ways I can pull an ace out of the deck. And in the denominator, that's the number of cards that we might pull out that are not an ace. Well, 52 minus 4, that's 48. There's 48 cards that are not an ace. So our odds would be 4 over 48. Or you can reduce this fraction. This is 1 over 12. So what are the odds that an ace is drawn out of a deck of cards? 1 out of 12. So what are the odds that an ace is not drawn out of a deck of cards? Well, remember, this is just the reciprocal of what we found before. In the numerator goes all the possible occurrences, or the number of possible occurrences, that don't give us the result we're looking for, which is an ace. So there are 48 cards that are not aces. Then in the denominator are the number of outcomes that are possible, or the 4 aces in our deck. So what are the odds that an ace is not drawn out of the deck of cards? 12 over 1, or 12 to 1. Now let's go back to talking about probability. There are several different types of probability, and the first one we're going to talk about is the theoretical probability. The theoretical probability occurs when we know all the total number or possible outcomes of an event. So what is the probability of rolling a 4 with a 6-sided die? Well, a 6-sided die has 6 numbers on it: 1, 2, 3, 4, 5, and 6. So what is the probability of rolling a 4? Well, that's when we roll our die and we get a 4. That only occurs once out of 6 total possible outcomes. So the probability of rolling a 4, that's 1 over 6, or 0.16 repeating. What would be the probability of rolling an even number with a 6-sided die? Well, we know all 6 possible outcomes of rolling a 6-sided die, and the even numbers are 2, 4, and 6. So our probability would be the number of outcomes that are even, so there's 1, 2, 3 of them, and the total number of outcomes, well, there's 6 of those. So we have a 3 over 6, or you can reduce that down to 1/2. So our probability of rolling an even number with a 6-sided die would be 1 over 2, or 0.5. So even though we're talking about theoretical probability, the way we solve for the probability is exactly the same. This is just the theoretical probability because we know every possible outcome of the total number of outcomes. Another type of probability is the experimental probability. Experimental probability comes from when we do many experiments and we get a probability of certain events in that experiment from happening. Then, if we were to conduct another experiment, we would assume that the probability of getting a certain result from that next experiment would be the same probability that we found from the previous experiments. Let's look at this example. Here we've surveyed several adults, and we surveyed them on the amount of time they spend watching TV per day. 79 of the adults watched less than 1 hour. 104 watched between 1 and 2 hours. 198 watched between 2 and 3 hours. 211 of them watched between 3 and 4 hours, and 312 of them watched for more than 4 hours. So what's the probability that a surveyed adult, if we surveyed another adult, watches more than 2 hours of television per day? Well, we don't know the probability of that particular adult. So what we do is we assume that the probability that this adult watches more than 2 hours of television per day is the same probability of all the other adults that we already surveyed. So to find this probability, we need to find all the total outcomes of adults that watch more than 2 hours. Well, these 198 adults watch more than 2 hours. These 212 adults watch more than 2 hours. And these 312 adults watch more than 2 hours of television. If we add that up, 198 plus 211 plus 312, that's equal to 721 surveyed adults that watch more than 2 hours of television. Now this is over the total amount of adults that have been surveyed, or the total possible outcomes. So we take this 721 and we add the adults that didn't watch more than 2 hours of television a day, so these 104 and these 79. That's 904. So that's the total number of possible outcomes. If you do this division, you'll come up with a decimal. That's approximately 0.80. So what's the probability, or the experimental probability, that a surveyed adult watches more than 2 hours of television a day? Well, according to the data in this experiment, there's a 0.8 probability that the next adult surveyed will watch more than 2 hours of television per day, or an 80% chance that the next surveyed adult is going to watch more than 2 hours of television per day. Now again, we calculated our probability exactly the same way we always do. This is just the experimental probability because the probability of the next event is based on the previous events or the previous experiments. Well, now that we know how to find the probability of a single event, or the simple probability, let's talk about finding the probability when more than one thing happens at a time, or the probability of multiple events. When we talk about the probability of multiple events, we often illustrate these different probabilities using a Venn diagram. This green box in front of us is a Venn diagram. The green box represents every possible outcome. The blue ellipse represents the probability, or the outcomes, that satisfy event A. The red ellipse satisfies all the events, or the probability, of event B. And this overlap in purple here is all the events that satisfy, or all the outcomes that satisfy, event A and event B at the same time. So let's look at an example of this. Let's say event A, that is pulling a heart out of a deck of 52 cards. Let's say event B is pulling a face card out of a deck of 52 cards. If you counted up every dot in this Venn diagram, the green ones, the blue ones, the red ones, and these purple ones, you would find out that there are 52 dots in this Venn diagram. Each one represents one card in a deck of 52 cards. All the blue and purple dots here inside this blue ellipse represent event A. If you were to count them up, you would find out that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cards that satisfy event A. Well, event A is pulling a heart from a deck of cards, and there are 13 hearts in a deck of cards. If you were to count up all the dots in the red circle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you would find out that there are 12 cards that satisfy event B. Well, event B is pulling a face card from a deck of cards, and there are 12 face cards in a standard deck of cards. Now, in the middle here, these purple dots, these are the cards that satisfy both event A and event B. These three dots represent the three cards that are both hearts and face cards. One of these dots is the King of Hearts. The other one would be the Queen of Hearts. And the last one would be the Jack of Hearts. So the three dots, again, in the intersection of these two ellipses satisfy both event A and event B, their hearts and their face cards. So now we know what a Venn diagram is. Let's just talk about some vocabulary that's common when we talk about the probability of compound events. If we say the union of event A and event B, or sometimes we'll say the probability of the union of A and B, union is represented by this U. That just means all of the events that satisfy both A and B. So we'd want all of the cards that are both hearts and face cards. If we say the intersection of A and B, or sometimes you'll see it as the probability of the intersection of A and B, and it's indicated by this upside down U, that just means all of the outcomes that are in the intersection of our Venn diagram, or that satisfy both A and B. In this case, the intersection of A and B, if we were talking about hearts and face cards, the only cards that satisfy the intersection of these two events are the King of Hearts, the Queen of Hearts, and the Jack of Hearts. Sometimes you'll hear that two events are disjoint events or mutually exclusive. That means that if we were looking at their Venn diagram, our ellipses do not overlap. That also means that there are no outcomes that satisfy both events. For example, if we said event A was pulling a 7 from a deck of cards and event B was pulling a 9 from a deck of cards, well, there are no cards that are both 7s and 9s at the same time. So there are no cards that we can pull out that would satisfy pulling a 7 and pulling a 9 at the same time. Those events are mutually exclusive or disjoint events. So now let's talk about the probability of two events. If we said we wanted the probability of A or B happening, well, that's equal to the probability of A plus the probability of B minus the probability of A and B. Or you can think of this as the probability of the intersection of A and B. So, if event A is pulling a heart from a deck of cards, and event B is pulling a face card from a deck of cards, well, we can find the probability. We count up all of our points. There are 52, because there's 52 cards in a deck. In event A, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cards that satisfy event A. So the probability of A would be 13 over 52. Now we look at the probability of event B, the probability of pulling a face card. Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different face cards in the deck of cards. So our probability of B would be 12 over 52. If we add these two probabilities together, we'd end up with 13 over 52 plus 12 over 52. That's equal to 25 over 52. Except the probability of A or B is not 25 over 52. Let's count up all the points that are in event A and B. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2. There's only 22 cards that satisfy A or B. So the real probability of A or B, this is 22 over 52. And the reason why we got 25 before is because when we added the probability of A to the probability of B, we counted these three items or these three cards twice. But we're not going to pull these three cards out of the deck of 52 twice. We can only pull them once. They only exist once. So that's why we always subtract this intersection, or the probability of A and B happening at the same time. That just keeps us from double counting the outcomes that satisfy both events. So if we ever want the probability of A or B, that's just equal to the probability of A plus the probability of B minus the probability that both A and B are satisfied, or the intersection of A and B. So what is the probability of pulling a single card out of a deck of 52 that is a heart or a face card? Well, we just did this. Remember that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, or the intersection of A and B. Now, A is pulling a heart, and the probability of pulling a heart is 13 out of 52. We're going to add that to the probability of B, and the probability of B is pulling a face card. Well, that's 12 out of 52. And then we're going to subtract the probability of A and B together. Well, that's just these 3 out of 52, so 3 out of 52. So we have 13 out of 52 plus 12 out of 52 minus 3 out of 52. All three of these fractions have the same common denominator, so we can just add and subtract our numerators. 13 plus 12 is 25, subtract 3, and we got 22 out of 52. This reduces down to 11 out of 26. So the probability of pulling a heart or a face card out of a standard deck of 52 is 11 out of 26. If you want to put that in decimal form, that's 0.423 approximately. So we have a little bit over a 42% chance of pulling a heart or a face card out of a deck of 52 cards. So now let's try finding the probability of some disjoint or mutually exclusive events. What is the probability of pulling a single card out of a deck of 52 that is a face card or a 7? Well, once again, we can use our formula. The probability of A or B, that's equal to the probability of A plus the probability of B minus the probability of both A and B happening. Let's say that event A is pulling a face card. So this is event A. Probability of pulling a face card from a deck of 52, that's 12 out of 52. So we found the probability of event A, and now we need to find the probability of event B. Let's say event B is pulling a 7 out of a deck of 52. Well, there are 4 7s in a standard deck of cards, so our probability would be 4 out of 52. Now we need to subtract the probability that the card we pull is both a face card and a 7. Well, there are no cards that are face cards and a 7, so that would be 0 out of 52. Again, these all have the same common denominator, so we can add and subtract our numerators. 12 plus 4 is 16, minus 0 is still 16, so 16 over 52. This reduces down to 4 out of 13, so our probability of pulling a face card or a 7 is 4 out of 13, or you can put that in decimal form, and that's a little bit less than 31%. Now the last thing we have to talk about is the probability of complementary events. Here we have the probability of A with this line over it. This basically means this is the probability of A not happening. And the probability of A not happening is equal to 1, the 100% probability, minus the probability of A happening. So what's the probability of being dealt a spade from a deck of 52 cards? Well, there's 13 spades in a deck of 52 cards, so our probability would just be 13 over 52. This reduces down to 1/4, so the probability of being dealt a spade from a deck of 52 cards is 0.25. So what's the probability of not being dealt a spade from a deck of 52 cards? Well, there are 39 cards that are not spades in a standard deck of cards. So it would be 39 out of 52. This reduces down to 3/4. So the probability of not being dealt a spade from a deck of 52 cards is 0.75. Now, if you didn't want to count up all the cards that were not spades, instead of solving it this way, you could have just found the probability of being dealt a spade, which is 0.25, and then subtracted that from 1. And you would have got 0.75, or the probability that you got before when you counted up all the cards that were not spades. So that's how you can use complementary events to find probabilities of different events by finding the probability of an event not happening. And that completes the tutorial on the probability of compound events.